Hello, viewers. In today's session, we are going to discuss the concept of node as a double point, right? So, with the help of this problem, we are going to discuss the nature of double points on the curve whose equation is given as x cube plus x square plus y square minus x minus 4y plus 3 is equal to 0. So, here will restrict ourselves to the double point which is known as a node, right? So we'll here prove that this equation or this curve has a node as a double point, and we'll also discuss the necessary and sufficient condition for a curve to have a double point as a node, right? So we'll see the working rule, how to prove that this given curve has a node as a double point. So let us first quickly see the definition of double points and the definition of a node as a double point. So let us first consider the definition of double points, right? So a point on a curve through which two branches of the curve pass is called a double point. For example, let us consider a curve like this. Suppose we have a curve like this, and here we can see that at this point P, we have two branches of the curve, right? So let us consider the equation of the curve as f of x comma y is equal to 0, or simply f is equal to 0. So this is the equation of this curve, and here we have two branches. The first one is this and the second one is this. So a point on a curve through which two branches of the curve pass is called a double point. So here P is a double point because here two branches of the curve pass, right? And let us now consider the definition of node, right? So if two branches of a curve pass through a point P, and if we draw two tangents at P and the tangents are real and distinct, then this point P is called or it is known as a node, right? Suppose at this point P we draw a tangent like this, and suppose this is the tangent, say T1, and if we draw another tangent at this point P like this, suppose this is the another tangent, and let us call this tangent as say T2, right? So if two branches of a curve pass through a point say P, and if two tangents are drawn at this point P, say T1 and T2, and both the tangents T1 and T2 at P are real and distinct, then this point P is known as a double point as a node, right? So this point P is a double point because at this point P we have two branches of the given curve, say f of x comma y is equal to 0, and if we draw two tangents at this point P, that is say this tangent T1 is to this branch and this tangent T2 is to this branch, then if both the tangents are real and distinct at this point P, then this point P is known as a node. So now let us consider the conditions when a given curve has a double point as a node, right? So in this problem, we are going to show that this curve has a double point as a node, right? So let us now consider the coordinates of this point P as say A comma B, right? And the necessary conditions for having a double point on a given curve are del f over del x is equal to 0, del f over del y is equal to 0, and f of x comma y is equal to 0, right? So the necessary condition for having a double point is that the partial derivative of f with respect to x is equal to 0, the partial derivative of f with respect to y is equal to 0, and this point p, that is the coordinates say x comma y, it must satisfy the equation of the given curve, right? And this point p to be a node, we have the condition that is del square f over del x del y uh, square should be greater than del square f over del x square times del square f over del y square, right? So here we are going to make use of this working rule to find out this point p as a node, right? So for having a double point on a given curve, we have del f over del x is equal to 0, del f over del y is equal to 0, and f of x comma y is equal to 0. That is this point p, uh, which has the coordinates a comma p, it must satisfy the equation of the given curve, right? And for this point p to be a node, we must have this condition, that is the square of del square f over del x del y should be greater than the product of the second order partial derivatives of f with respect to x and with respect to y. So now let us first write the equation of the given curve as f of x comma y. Here we have x cube plus x square plus y square, and here we have minus x minus 4y plus 3, right? So let us now first find out del f over del x. So here we have to take the partial derivative of f with respect to x. So here we have 3x square, here we have 2x, here we have 0 because this is y square, that is we do not have here any term containing x, right? And here we have the partial derivative of x with respect to x is 1, here we have 0, and here we have 0. So we have 3x square plus 2x minus 1, and then we find del f over del y, the partial derivative of f with respect to y. So here this derivative is 0, here also we have 0, here we have 2y, and here we have 0, then we have here minus 4 times 1, and then we have 0. So here we have a 2y minus 4, right? So now we have del f over del x is equal to 0, and del f over del y is equal to 0. So now we have two equations, right? So the first one is 3x square plus 2x minus 1 is equal to 0. Then we have 2y minus 4 is equal to 0. So we can now solve this quadratic equation. So here we can make use of the method of splitting the middle term. So we have 3x square plus 3x minus x minus 1 is equal to 0, 3x x plus 1 minus 1 x plus 1, and x plus 1 and 3x minus 1 is equal to 0. So from here we have x is equal to minus 1, and from here we have x is equal to 1 over 3. That is, we have x plus 1 is equal to 0, which gives us x is equal to minus 1, and 3x minus 1 is equal to 0, it gives us x is equal to 1 over 3. And from here we have 2y is equal to 4, so y is equal to 4 over 2, that is 2, right? So here we have x is equal to minus 1 and x is equal to 1 over 3 and y is equal to 2, right? So now we have the points, that is minus 1 comma 2. So first pair is minus 1 comma 2 and the second pair is 1 over 3 and 2, right? So now let us check that whether these 2 points satisfy the equation of the given curve. So now let us substitute this coordinate in the equation of the given curve. So x is minus 1 and y is 2. So we have this expression, right? So minus 1 cube. Here we have x is equal to minus 1. So here we have minus 1. Then we have plus 1. Here we have 4. Here we have plus 1. Then here we have 8, 4 times 2, and here we have 3. So we have now here 4 plus 1 5 and 5 plus 3 8. So we have 8 minus 8 is equal to 0. So we have f of x comma y is equal to 0. So this point, it satisfies the equation of the given curve. So therefore this point is a double point, because here we have del f over del x is equal to 0, del f over del y is equal to 0, and f of x comma y is equal to 0, right? So we have this double point, that is minus 1 comma 2. Now let us substitute this coordinate in the equation of the given curve. So x is 1 over 3, y is 2. So here we have 1 over 3 cube. So here we have 1 over 27, and then we have 1 over 9. Here we have 4. Here we have minus 1 over 3, and then we have 8, and here we have 3. So we can now write 1 over 27, 1 over 9, and minus 1 over 3, collecting these three fractions here. And then we have 4 plus 3 7, 7 minus 8 is minus 1. So here we can take the LCM. So we have 1, then we have 3, then we have 9, and here we have minus 1. So this is 4 minus 9 is minus 5 over 27. Then we have minus 1. So this is minus 5 minus 27 over 27. So that is minus 32 over 27, and this is not equal to 0, right? So here we see that f of minus 1 comma 2 is equal to 0. So this point satisfies the equation of the curve, and f of 1 over 3 2 is not equal to 0, that is this is minus 32 over 27. So this point, it doesn't satisfy the equation of the given curve. So here this point cannot be a double point, right? So here we have only one double point, minus 1 comma 2. And now let us show that this point is a node, right? That is, if we draw the two tangents at this point to this curve, then we have two real and distinct tangents. So now minus 1 comma 2 is a double point. So let us now see whether this point, it satisfies this condition, because this is the condition for this point to be a node, right? So let us now find out this expression, that is this partial derivative del square f over del x del y. So we can write it like this: del over del x, and here we have del f over del y, right? Now del f over del y is 2y minus 4, right? So del over del x of 2y minus 4. Now we can see that this is a function of y only, right? So here we do not have any x, so the partial derivative of this expression with respect to x is 0, right? So at this point, that is del square f over del x del y, at this point, that is minus 1 comma 2, is equal to 0, right? So now let us find out the second order partial derivative with respect to x. So here we have del square f over del x square, that is del over del x of del f over del x, and del f over del x is we have here 3x square plus 2x minus 1. So here we have 3 times 2x, and here we have 2 times 1, here we have 0, right? So here we have this expression in terms of x only, right? So this is 6x, and here we have 2. So now let us find out the value of this second order partial derivative with respect to x at this point, right? So we have del square f over del x square, and here we have minus 1 comma 2. So x is minus 1. So we have 6 times minus 1 plus 2 minus 6 plus 2, that is minus 4, right? So now let us find out the second order partial derivative with respect to y. So we have del over del y, del f over del y, and we have del over del y, and del f over del y is 2y minus 4, right? So here we have 2 times 1, the partial derivative of y with respect to y is 1, and here we have 0, so we have simply 2. So the value of second order partial derivative with respect to y at this point, that is at the double point, we have del square f over del y square, and here we have minus 1 comma 2 is equal to 2, because this doesn't contain any x or y, right? So now we have the expression for del square f over del x del y at this point, minus 1 comma 2 is equal to 0, because this derivative is already equal to 0 and it doesn't contain any x or y. So the value of this partial derivative at this point is clearly 0, right? And del square f over del x square at this double point is minus 4, and del square f over del y square at this point is again here we have 2, because this expression doesn't contain any x or y, right? So let us now see whether this condition is satisfied by this double point to be our node. So now substituting this value as 0 in this expression, so we have 0 square, and then we have here del square f over del x square as minus 4, and here we have del square f over del y square as 2, right? So here we have 0, and here we have minus 8, right? And we see that this inequality is true, right? So 0 is clearly it is greater than minus 8. So the square of del square f over del x del y is greater than the product of these two second order partial derivatives. That is 0 is greater than minus 8 for this point minus 1 comma 2. So this point is a node because this double point it satisfies this condition, right? So this is the working rule how to examine the given curve for a node. Hello viewers, in today's session we are going to discuss the working rule, how to find the intervals where a given function is concave upward and concave downward, right? So with the help of this problem we are going to find out the points of inflection for this curve y is equal to x raised to 4 minus 6x square plus 5, and we'll see how the concavity changes at the points of inflection, right? So here we are going to see the working rule, how the concavity of a curve changes at the point of inflection. So let us first find out the first derivative of y with respect to x. So we have dy over dx is equal to 4x cube, and then we have minus 6 times 2x, and the derivative of 5 being a constant is 0. So we have 4x cube minus 12x. Now let us find out the second derivative, and the second derivative is given by 4 times 3x square, and then we have minus 12 times 1, so this is 12x square minus 12, right? So we can write it like this, we can take 12 common, so we have x square minus 1. Now the third derivative is given by here we have 12, then the derivative of x square is 2x, and the derivative of 12 is 0, so we have 24x. So the first step is to get the first derivative, second derivative, and the third derivative, right? Now at the points of inflection, the second derivative, that is d2y over dx2 is equal to 0, and the third derivative should not be equal to 0, right? So at the points of inflection, the second derivative is equal to 0, and the third derivative should not be equal to 0. So now when we equate the second derivative equal to 0, then we have this equation, 12 times x square minus 1 is equal to 0, x square minus 1 is equal to 0, x square is equal to 1. So x is square root of 1, that is plus minus 1. So here we have two values of x, that is x is equal to plus 1 and x is equal to minus 1. So we have 2 points of inflection, that is x is equal to 1 and x is equal to minus 1. So now let us show that the third derivative is not equal to 0 at these 2 points, right? So here the third derivative is 24 times x. So let us substitute x is equal to 1 in the third derivative. So we have here d3y over dx3, and taking x is equal to 1, we have 24 times 1, that is 24, which is not equal to 0, right? And the value of the third derivative at this point x is equal to minus 1, we have 24 times minus 1, that is minus 24, which is also not equal to 0. So x is equal to 1 and minus 1 are the points of inflection, right? So let us now find out the intervals where this function or this curve is concave upward and concave downward. So the condition for concave upward is given by d2y over dx2 should be greater than 0. So a curve or a function is concave upwards when the second derivative is positive, that is it is greater than 0. So this implies that the function dy over dx, that is the first derivative, should be an increasing function, right? So here for concave upwards we have this condition: the second derivative should be greater than 0. Now the second derivative is given by 12 times x square minus 1. This should be greater than 0. So here we are to find out the intervals where this function is concave upwards. So we have now x square minus 1 greater than 0 and x square is greater than 1. So now let us solve this inequality. So we can now write x square greater than 1 square. So this inequality is of this form, that is x square greater than say alpha square, right? And here the value of alpha is equal to 1, and we know that the solution of this type of inequality is given by x belonging to the interval minus infinity to minus alpha union alpha to infinity. So we have now alpha is equal to 1, so we have minus infinity to minus 1 union 1 to infinity, right? So in this interval the function is concave upwards, and we can also write it like this, that is x is less than minus 1 and x is greater than 1. And now for concave downwards we have the condition that is the second derivative should be less than 0. So a function or a curve is concave downwards when the second derivative is less than 0, and this implies that the first derivative, that is dy over dx, should be a decreasing function, right? So now d2y over dx2 should be less than 0, that is the second derivative should be negative. So we have now the second derivative 12 times x square minus 1 less than 0. So we have x square minus 1 less than 0, x square less than 1. So we can now write here x square less than 1 square, and this inequality is of this form, that is x square less than alpha square, right? So this inequality is of this form where alpha is now 1, and the solution of this type of inequality is given by x belonging to the interval minus alpha to alpha, right? So we have the solution of this inequality as x belonging to minus 1 to 1, or we can write x greater than minus 1 and less than 1. So in this interval the function is concave upwards, and in this interval the function is concave downwards, that is x should be greater than minus 1 and less than 1. So now let us draw the real number line. So here we have minus infinity, here we have plus infinity, and here we have minus 1, and here we have plus 1, right? So we see that the function is concave upwards when x belongs to minus infinity to minus 1. So in this region, the function is concave upwards, right? And here we have the interval 1 to infinity. So here also the function is concave upwards, right? And in this interval minus 1 to 1, that is this interval minus 1 to 1, the function is concave downwards, right? So here with the help of the real number line, we have shown that in the interval minus infinity to minus 1 union 1 to infinity, the function is concave upwards, that is the second derivative is greater than 0. And in this interval minus 1 to 1, that is when x is greater than minus 1 and less than 1, the function is concave downwards, that is the second derivative is less than 0. And these points, these 2 points, minus 1 and plus 1, are the points of inflection, right? So from this real number line we can easily conclude that the concavity changes at x is equal to minus 1 and x is equal to plus 1, which are the points of inflection, right? So a point is known as a point of inflection when the second derivative is equal to 0 and the third derivative is not equal to 0, and moreover there must be a change in concavity of the curve, that is the curve must change its concavity either from concave upward to concave downward or from concave downward to concave upwards. Then only we have a point of inflection. And from this real number line we can easily conclude that, or we can draw the conclusion that at this point, that is minus 1, the concavity changes, that is from concave upwards to concave downwards. And at this point plus 1, the concavity again changes, that is from concave downwards to concave upwards, right? So there is a change of concavity of the curve. At these points, the points are the points of inflection, that is x is equal to minus 1 and plus 1, right? So here at x is equal to minus 1, the concavity changes from concave upwards to concave downwards. And again at x is equal to plus 1, the concavity changes concave downwards to concave upwards. So now we can summarize our discussion. So at x is equal to minus 1, the concavity changes from concave upwards to concave downwards. And at x is equal to plus 1, the concavity changes from concave downwards to concave upwards, right? So the shape of the curve, it goes like this. At x is equal to minus 1, so the concavity changes from upward to downward. So the shape of the curve, it is like this, right? So this is concave up and this is a concave down. And at this point, that is x is equal to minus 1, which is the point of inflection, right? So the concavity changes from up to downward. At this point x is equal to minus 1, and at x is equal to plus 1, the concavity changes from downwards to upwards. So in this case the shape of the curve, it goes like this, right? So here we have the point of inflection, x is equal to plus 1, and here the concavity changes from downwards to upwards, right? So this is how we can show that the concavity changes from upward to downwards or downwards to upwards. And we can also make use of the second derivative to show that how the concavity changes at the points of inflection. So now let us show that how the concavity changes with the help of the second derivative and taking 2 points in the neighborhood of the points of inflection. So let us first take this point x is equal to -1, and let us take 2 points in the neighborhood of x is equal to -1. So here we have -1 minus h, and here we have -1 plus h. Now the second derivative can be written as 12, and here we can write x minus 1 x plus 1, right? So here we can now see the sign of the second derivative as we move from this point -1 minus h to -1 plus h. So we have the second derivative, that is this may be taken as f double prime of x if we take the function y is equal to f of x. So here we have -1 minus h. So let us calculate the sign of second derivative at these neighboring points. So we have here 12, then we have -1 minus h minus 1, then we have -1 minus h and plus 1. And remember, this h is infinitesimally very small and it is greater than 0. So here we have 12, then we have -2 minus h, and here we have simply minus h. So we have here 12h, that is 12h, and multiplying this term by negative sign, so we have 2 plus h. Now we can see that this is positive and this is also positive, right? So the combined sign or the overall sign of the second derivative at this point is a positive. And when the second derivative is positive, then the curve is concave upwards. So here we have concave upwards, and the second derivative at this point -1 plus h, we have 12 minus 1 plus h minus 1 minus 1 plus h plus 1. And here we have 12, then we have h minus 2, h minus 2, and here we have simply h. Now see, h is greater than 0, but it is less than 1. So this quantity is negative and this is a positive because h is a positive quantity. So here the overall sign of this term is a negative, right? Negative times a positive is negative. And when the second derivative is negative, that is it is less than 0, then the curve is concave downwards. So here the second derivative is less than 0, so here we have concave downward, right? So we see that as we go from -1 minus h to -1 plus h through x is equal to -1, then the sign of second derivative changes from positive to negative, right? That is the curve changes its concavity at this point from concave up to concave down. So here the concavity changes from concave up to concave down, right? And similarly for this point, that is x is equal to +1, we have here x is equal to +1, we have 2 points, 1 minus h and 1 plus h in the neighborhood of x is equal to 1. So let us now calculate the change in sign of second derivative as we move from 1 minus h to 1 plus h through x is equal to 1. So now here we have f double prime and 1 minus h. So we have 12 1 minus h, and here we have minus 1, then we have 1 minus h plus 1. So we have 12, here we have minus h, and here we have 2 minus h. Right now, see, 2 minus h is positive because h is less than 0, less than 1, right? So h is greater than 0, but it is less than 1, and it is infinitesimally very small. So 2 minus h is positive. Here we have a negative because here we have a negative sign, so the overall sign is negative. So the second derivative is negative, and when second derivative is negative, then uh, the function is concave downwards. So here we have concave downwards, and similarly here we have 1 plus h. So we have 1 plus h, 12, taking 1 plus h in place of x. So we have 1 plus h minus 1, 1 plus h plus 1. So we have here 12. Here we have 1 minus 1 is 0. So h. Then we have 2 plus h, and 2 plus h is positive, h is positive, so the overall sign is positive, right? And when the second derivative is positive, then we have the function as concave upwards, right? So we see that when we go from 1 minus h to 1 plus h through x is equal to 1, then the sign of second derivative changes from negative to positive. That is, the concavity changes from concave down to concave up, which is shown over here. So at x is equal to plus 1, the concavity changes from concave downwards to concave upwards, because the sign of second derivative changes from negative to positive when we move from 1 minus h to 1 plus h through x is equal to 1. And similarly here, at x is equal to minus 1, the sign of second derivative changes from positive to negative. That is, the concavity changes from concave upward to concave downward when we move from minus 1 minus h to minus 1 plus h when through x is equal to minus 1, right? So here x is equal to 1 and minus 1 are the points of inflection, because the concavity changes from upwards to downwards, or from concave downwards to concave upwards.